Today we want to look at how to find the volume when you take a region in two-dimensional space and revolve that region around an axis. So to start off, say f of x is a continuous function on the interval from a to b. And let's revolve the region between f and the axis. So we want to look at y from 0 to f of x and x from a to b. Let's do the x-axis. So let's take a look at what that might look like. So we'll have some curve, and you could draw this however you like, but make it something that you could easily draw a picture of it revolving, so I won't make it too complicated. So this is my y equal f of x going from a to b. And so there's my region. Between the curve and the axis and from a to b. Now we're going to take that region and spin it around the x-axis. And as we do that, we'll create a solid. So to get a sketch of what we're looking at, I'm going to draw a mirror image of that curve on the other side of the x-axis. And then just to get a sense of 3 dimensions, draw the ends on it there. So we have this volume. It's solid, right? Because this region, everything between the curve and the axis is getting revolved, so that's solid. You couldn't put your hand through there. We're interested in figuring out what the volume of that object is. So we'll go about this the same way we did for area. We'll start off by partitioning our partitioning our axis here, the interval from a to b, and then creating our rectangles. But now we'll take those rectangle approximations and revolve those around the x-axis. So you'd have some partition here from a to b, and I'll just look at one arbitrary from x sub k minus 1 to x sub k. Remember, you pick some point in between there, c sub k. And we'll assume that our function is constant over our subinterval from there to there. Now we revolve that rectangle instead of the curve. So I'll draw a mirror image here. And when I revolve that, we're going to have a right circular cylinder, right? Because when you take a rectangle and revolve it, it'll sweep out a cylinder. Well, what is this cylinder? It's got a height here. That's just our change in x. And this dimension here, the radius, well, the radius is being determined by the curve. It goes from the axis to here, or from 0 up to whatever our function is at c sub k. So let's write what would be the volume of this one little cylinder. I'll call that v sub k. And so for a right circular cylinder, it's pi r squared h. And as I said, the radius is this distance, which is just the function's value at c sub k squared, and then the height of our cylinder, the cylinder's on its side, so this is its height, delta x sub k. Now, we would have n of these cylinders, right? Each one of these subintervals would create a rectangle. That rectangle would revolve, creating a different cylinder. So we'd have a stack of cylinders that would be approximating that volume. And so the volume we're after would be approximately the sum, k from 1 to n, of all these v sub k's. That would be us adding up the volume of all those little cylinders. And then that volume would become exact when we let the norm of the partition go to 0 of these v sub k's, which is this. And as we've seen before, this is the definition of the definite integral. So this is equal to the integral from a to b of pi f of x squared dx. So now we have our volume expressed as an integral. And if you look at this, what are we really integrating? This is a radius of revolution, right? As you go around at any point along this object, if you pick any point and revolve that point, you're going to get a circle. The radius of that circle is the value of the function. So a way of thinking of this is to get volume, you integrate area, where this area is cross-sectional area. So the cross-sections, when you revolve and slice like this, those cross-sections are circles. The area is pi r squared. So simply integrate the cross-sectional area to get the volume. And as we saw before with area, we know that this limit converges on the volume so long as our upper approximations and lower approximations converge to one another. And we're guaranteed to get that by having our function be continuous over that interval. So next time what we'll do is we'll look at an example with some actual curves of finding this volume by taking cross-sectional slices.